can I start? Okay. Yeah, thank you so much for first all organizer for this great opportunity to give a talk today, and also this is the second part of the talk in September. If you were here in September, and so we finally finished writing our paper, and we submitted to a journal. So now I can officially give a talk, and this is joint work with called Ake Meyer, Peter Huggins, and Leo Pachter. So, all right. I hope. Okay. So I would like. So we know that Mike Steele and Oliver Guasquare showed that neighbor-joining method is a greedy algorithm for finding balanced minimal evolution trees, and this means that neighbor-joining method actually belongs to a class of several techniques which iteratively improves the balanced balanced minimal evolution tree length by modifying the tree. So more specifically, that if you have a pairwise distances, so distance matrix, and neighbor-joining method starts with a start-like tree and then repeatedly pick a cherry neighbors, and the resulting the largest decrease in a BME tree with the length d times the w tau, and tau is some tree topology, and wij tau is given by this. And so our motivation is that how good of this greedy algorithm neighbor joining is for BME. So in the other word, how often neighbor joining method recover the BME tree. Okay, so this is our motivation. So this is a review for neighbor joining method. So this is really fast and consistent. So input is the pairwise distances, and presume that this is arise as a perturbed tree metric, and output is the tree topology, which induces a tree matrix that is hopefully close to the input matrix. And intuition is that we want to find two nodes which is a close or neighbor and join them as a cherry in a tree. So actually neighbor joining nodes, so for the nodes A, B, we have the Q criterion that is defined by QAB. That's a Q I defined n by n matrix. That is n minus 2 times DAB. So this DAB is the AB's entry of this D, and minus all sum of DAK plus DBK. And so those and then later, AB, so this Q criterion says, so we want to find the smallest entry of this Q, and then, if QAB is the smallest element of this Q, then ABs are, we say that that's a cherry, and then replaced by a single new node G that is actually a unique internal node on a path between A and B. And then we calculate the distance GK, and that is defined by this, and we replace the actually AB with this single node G, and then we have the node n minus 1 nodes, and recursively we apply the same process. Okay, so yeah, so we're gonna use so instead of using the directory original distance matrices, we use these Q values. Okay. So neighbor joining method is consistent. That means that if we have the additive matrix or additive tree that's the input, then it returns the additive tree. But however, usually we estimate distance matrices by MLE or other method, so that those distance matrices are not tree metric usually. So So neighbour-joining returns a tree topology which induces a tree matrix that is hopefully close to the input. So question is, which distance matrices with the neighbour-joining returns a particular tree topology? So that means that if we have a particular tree topology, I would like to know the set of all distance matrices that gives a particular tree. Clear? Okay. Okay. So all right. So now like we look at really closely Q criterion. Then we notice that Q criterion gives a linear inequalities. And after picking a cherry and replacing a new node, this gives equations. So we look at staring at this. So we have a set of inequalities and a set of equations, and then so the neighbor-joining method will output a particular tree topology tau. Then we pick a cherry in a particular order. So we have some order of picking a cherry. So even though we have a same tree topology, we have different way to get the tree topology, right? So if we fix the actually particular order and tree topology, then neighbor-joining method output some particular tree topology and particular order if only if the original distance matrix Dij satisfies certain linear equalities, given namely that just Q criterion and also reducing the dimensions equations. So this is because that if we change, even though if you have a certain tree topology, if you pick a different way, it's gonna give you different inequalities and different equations, so that you have to fix the disorder. And these inequalities define a cone in a R2 and choose 2, which we call the neighbor-joining cone. Okay? And the neighbor-joining cone will output a particular tree topology tau if only if a pairwise distance this D is inside of R to the N to the 2 lies in a union of neighbor-joining cone, some union of neighbor-joining cone. Okay? So because that like I said, if you change the different order, then it's gonna have different cones. So you have to take the union of the neighbor-joining cone. Okay, so for example, for n equal 4, this is simple because just only one, cherry picking, so that this is actually really nice, and this actually cone looks like this. Actually, that's a two-dimensional cones, and we have 3 cones. So this actually particular cone, this gives this 3, and this gives this 3, and this gives this 3. Actually, this dimension of this cone is usually, I didn't say that, but in a last talk I talked about this. By shifting lemma, that is n choose 2 minus n. So that's the dimensions. So this case, it's n choose, so that is equal to 4 choose 2 is 6 minus 4, so this is 2 dimensions. Okay, so the issue with neighbor-joining method. So neighbor-joining method is very fast and consistent, but it is based on the model speciations. So this is not actually okay. Of course, like pairwise distances are actually based on model, but neighbor-joining method takes distance matrices, and also that until recently we didn't know that it's not clear that neighbor-joining method what they are optimizing, and if at all. And also the neighbor-joining method outputs a tree topology tau if only if data lies in union of the cone, but the union of the cone not need to be convex. Actually, they are not convex after n equal 5. Okay, n equal 4, that's convex. But after n equal 5, it's not convex anymore. So that means that there are distance matrices actually in a preprint. You can download at the archive, but and we wrote some example that is D and D dash are actually distance matrices such that neighbor-joining method produces the same tree topology, but if you take that sum and divide it by 2, that gives you distance matrix, but that returns a different tree topology. So I picked this D from one cone and D dash from the other cone, and I add, and that's not a union, that's not convex, so that's gonna give you different tree topology. So that's not really nice actually. And yeah, we don't know how we have some formula, but we don't know the combinatorial description of the cone so well. Okay, so now I'm gonna switch to the BME method. So this is BME method is also a distance-based method, and also the weighted least method to find the closest tree matrix such that the total branch length of the tree is smallest. And using the Poplin formula, so basically based on its tree topology and estimated distance matrix D, that is Dij, and BME is to find tau such that minimum of all possible tree topology for D times W tau T, and Wij tau is given by this. So that's Poplin's formula. And so for example, just to make sure everyone knows that this W, that's weight. So that, for example, if I have this tree topology, then I can get this vector. Okay. So because like we have like one, so this is order 1, 2, lexicographically I order, and then that's like, okay, we have 1, 2, that we have 2 branches, and so 1 minus 2 is -1, so 2 times -1, 2 to the -1 is 1/2, and so on. Okay, so all right, so if you're staring at the facts we have, you can see this one as a linear programming, such as minimizing D times, so this is vectorized distance matrix, times X. X is in a convex hole of this guy, W tau I. And we call this actually polytope, BME polytope. Okay? So we are trying to find the combinatorics of the BME polytope. So using polymec, so this is called F vector, that's vertices, and that's actually edge, and this is facet, that's a facet, and so on. So yeah, so for n equals 7, we finally computed these informations. But we are really interested in actually combinatorial descriptions of edges. I'm gonna tell you why in a second. So so 4, 5, 6, 7, we have computed, and we don't know this actual value at all because this polytope is actually monster. It is really bad polytope, and especially like until 6, it was complete actually graph. That is a vertex is adjacent to all other vertices, and that's not really pretty at all. So, but the 7 actually, there is someone, no, actually it's not anymore complete graph. So we are curious that, okay, what's a combinatorial description of edges? I mean, we can compute brute force way, we can compute the, BME polytope, but I would like to know that what's the edge combinatorial description of edges, and what do you mean that? Okay, so edges and non-edges of the BME polytope. So still we don't understand what's going on. That means what the edges means. So each vertices represent actually each tree topologies. So that means the edges means that we are changing one tree topology to the other tree topology. So that means that something like a tree walk. So that's like if you have the tree move basically. So so if we understood the edges, then we might be able to devise a competitive alternative method like FastME, so improving by walking along the edge on a BME polytope. So that rather than near NNI moves or anything, and also that it's called simplex method in linear programming. This is a very efficient practical method. So maybe if we know that those edge moves, then we can actually apply simplex method on this polytope. Okay. So now I'm going to talk about BME cones. So for bifurcating tree topology tau, BME cone of tau is defined a set of all choice of distance matrices for which the tau minimizes the product D W tau. So in terms of like algebra or in terms of like combinatorics, this is the normal cone at the vertex tau, and actually W tau of the BME polytope. And the edges, so like I said, the edges of the BME polytope from the vertex, this guy, determines the facet of the BME cone of tau, and the facet of BME polytope that defines the extreme rays of the BME cone of tau. So that's a duality. And also nice thing is that BME cones are convex, not like neighbor-joining cone. So this is very nice, and actually in terms of like again commutative algebra, that's actually normal funds of the BME polytope. And like I said, so that means that BME method out of the tree topology tau for the two inputs D dash, and D dash are actually then this BME polytope BME method will also output tau on an input D plus D dash over 2 because that's convexity. Clear? So this is very nice. Okay, so what time is it? Okay, I have still time or not. Okay, I have to be in a hurry. Okay, so that we compare the BME cones and neighbor-joining method cones, and that is how we're gonna compare this, because like those are cones, but we do this taking the union of the unit sphere, and then we compare the actual volume of the spherical polytope for BME cone and neighbor-joining cone, union of the neighbor-joining cone, and then we took the ratio of it. And the method is basically like we approximated traditional Monte Carlo method and polyhedral algorithm. And so the quick summary of this guy, so the ratio is the neighbor-joining method and BME tree topology is 100% for 4 and 98% for n equals 5, 90 for n equals 6, 80 for n equals 7, and 65 for n equals 8. And also the weird thing is for n greater than equal to 7, then neighbor-joining method have difficulty to recover the BME tree for caterpillar tree. And we don't know why, actually. All right, so this is the future work, and so like I said, caterpillar tree have most difficult for recovering BME trees for neighbor-joining method, so we don't know why. And also that in general, yeah, so okay, I'm gonna skip this one. So I would like to compare not only neighbor-joining method and BME method, but also for the tree matrices, and how much, like how we can actually, like, okay, so I wanna compare that with tree matrix. And then also the edge, I would like to really, I'm working with Peter right now, that I would like to have the combinatorial description of the BME polytope for edges. Yeah, so anyway, thank you so much, and our paper is on the archive, so thank you for your attention.
I was just wondering, I don't know, but I was just wondering if we have heard this talk, I mean, yesterday or the day before, about that the lower bound for the, when neighbor join actually it is consistent, but you need a certain sequence length to make it, to make it reconstruct the right tree with high likelihood. And there we've seen that, I guess, the caterpillar trees are the worst ones. Mm-hmm. And then now you're telling with this respect to the BME thing, the caterpillar trees seem to be also the worst ones. So is there a connection? Have you already explored this, or? Oh,
we haven't explored. Just we were actually focusing on the comparison between BME and neighbor-joining method. But that's a good point. And also, I think actually, like when we are writing paper for generalized neighbor-joining method paper, we notice that caterpillar has always difficulty. So I have some intuitions, but I don't want to say right now. Okay. But yes.
I just wanted to ask you whether it would make any difference if you considered those variants of neighbor joining, like bio-NJ or waiver joining. Would that make any difference? Or?
We haven't looked at. That's a good question. Yes, we have to look at. Yes, that's actually we haven't. Just we did purely. Just we started actually. I started working with this. Neighbor joining cone like this January, and in March at the Minnesota IMA meeting, I saw Biopactor, and just we started doing this. So I haven't really looked at deeply. So I'm sorry, I don't know.
Let's thank the speaker once again.